Okay, you're going to start going over the August 2015 Geometry Common Core exam. So we're starting off with problem number 1. And in order to get credit, you have to write down these properties that I've written down, or just the properties of a rectangle. So make sure to write that down. All the properties of a parallelogram apply. And also the diagonals are congruent, and it has 4 90-degree angles. All right, so the problem is, so make sure to write that down if you want credit. All right, so take a second, pause it, and write this down. Okay, it's saying a parallelogram must be a rectangle when its diagonals are perpendicular, its diagonals are congruent, the opposite sides are parallel, the opposite sides are congruent. So, knowing the properties of a rectangle, the diagonals are not going to be perpendicular. Now, that would be the case with a rhombus. So, number 1 is not going to be our answer. Diagonals being congruent, that is actually our answer, number 2. Let's look at the other ones. Opposite sides are parallel. Well, if you look at a rhombus, the opposite sides are actually parallel, but it cannot be called a rectangle. So you want to make sure and be careful about that. And also number 4, the opposite sides congruent. Again, with a rhombus, the opposite sides are congruent, but it is not a rectangle, so just be careful. Okay? All right, question number 2. It says we have triangle A prime, B prime, C prime is the image of triangle ABC, which means ABC would be the pre-image. Under which transformation will the triangles not be congruent? Keyword not. So don't read through this entire problem and and miss the word not. All right. So it's where will they not be congruent? So I have some notes for you guys to write down about transformations, and we have rigid motion transformations, and our 3 rigid motions are reflections, translations, and rotations. The important thing about this is when you have a rigid motion transformation, the size and shape of the figure is not going to change. So whenever you do a rigid motion transformation, your image will always be congruent to your pre-image. All right? So take a second to write these notes down. All right. So we have number 1, a reflection over the x-axis. Well, a reflection is a rigid motion, which means that the image will be congruent to the pre-image. So that is not going to be our answer. Translation to the left 5 and down course, again, that's a rigid motion transformation. Dilation, you don't see that listed here. A dilation centered at the origin with a scale factor of 2 means that the shape will, or the size will change. So that's actually going to be our answer. A rotation, again, is a rigid motion transformation, which means your image will be congruent to your pre-image. All right, so make sure to write these notes down to get full credit. All right, number 3 says if a rectangle below is continuously rotated about side W, which solid figure is formed? Side W will be this side over here. Now, you have to picture W staying in the same place and this rectangle being rotated around. I'm not a very good artist, but the best way I can think to describe it is if you have ever been to a big hotel and you can see the doors spin that you go in. I think most hotels have doors like this, but maybe you've seen them in a movie. Picture the doors spinning. That's a rectangle spinning. It's a close comparison. And what type of shape does that make? When they spin in a circular motion. So what type of solid would have a circular base and a circular feel to it from the top to the bottom? Well, it's definitely not going to be a pyramid. it's not going to be a rectangular prism. A cone has a circle on the base, but that's not going to be all the way up to the top. So we're definitely looking at a cylinder. All right, so think about, it's kind of hard to describe, but if you picture it, it will make sense. Maybe you can take an index card and just fix one of the sides and then rotate the rest around. You can see that it will create a cylinder type of shape or type of solid, okay? So just write down this one part and go on to the next one. All right, looking at number 4, it says which expression is always equivalent to sine x when when x is in between 0 and 90 degrees. That's what this means for all the angles in between 0 and 90, not including 0 or 90. All right, so here's some notes I want you to write down. And if I were on a test and I was doing this problem, one thing you'd want to know is how can I figure this out in the calculator? So I would pick an angle. So let's just say you pick 30 degrees. So ask yourself, which expression is always equivalent to sine of 30 when x is in between 0 and 90? So first thing I might do, go to the calculator and see what is the sine of 30 degrees. So it's 0.5, right? Now, I'm looking then for one of these expressions to be also equal to 0.5. Well, if I use 30 degrees, I can just maybe plug in 30 here, and 30 here, and 30 here, and 30 here. And just go through and see which one is equivalent. So I could do, all right, I'll do cosine of 90 minus the degree I chose, which is 30, so the cosine of 60. So the cosine of 60 is also 0.5. So at this point, I'm thinking number 1 is my answer. But let's just look at number 2, cosine of 45 minus 30. So that'd be the cosine of 15. So I do the cosine of 15. Not equivalent, so we know that that is not an answer, or not the answer for us. The cosine of 2x, or 2 times 30. That's okay. Well, I'm going to pause for just 1 second here. All right, back. Let's continue looking at number 4. So looking at the third answer choice. If we had chose 30, for number 3, we'd have to plug in the cosine of 2 times 30, which is equal to 60. So that might look familiar because that's the same thing that we did on number 1. And we saw that it is equal. So now we have 2 answer options. So let's go to number 4, and then we'll look at the question a little bit more closely, see if we can see something else, all right? So we chose 30 degrees, so the cosine of 30 is, let's do cosine of 30 here, and that is 0.866. Remember, we were looking, our original angle was the sine of 30, which was 0.5. Now, so we've eliminated 2 of them. Now we have to go back because I got 2. When I plugged in 30, both the first answer and the third, those expressions both gave us 0.5. So now there must be something we're missing. Well, the thing is, you got to look at this word here. Very important word, always. It says is always equivalent. So when we chose 30 to plug in for x, that 2 of those expressions worked. Well, what if we chose 50? So let's choose a different answer, because it says it always has to work. So one of these expressions, either 1 or 3, is always going to be equivalent to sine x. and one of them, well, it was equivalent when x was 30. Maybe it would be equivalent at other points, possibly, but will it always be? So let's choose a different angle. What about 50? So let's do the cosine, I'm sorry, the sine. Remember, it's which expression is always equivalent to sine of x. So we want to start with sine of x, and let's just choose an angle. So I have sine of, let's do 50. We'll go to my calculator and see what the sine of 50 is. Right, sine 50 is 0.7660. Right now, if I go and plug in 50, this same angle, 50, into our third answer, which we have said is an option, it'd be the cosine of 2 times 50. So that's really going to be the cosine of 100. So now let's go back to the calculator. And what's the cosine of 100? Right, obviously not the same. That shows that the third expression, or the answer, the expression in the third answer worked with one angle, but it did not work with another one, which means it's not always going to be equivalent, which means our answer will be number 1. All right, so there you go on that. Okay, let's look at number 5. It says in the diagram below, a square is graphed in the coordinate plane. A reflection over which line does not carry the square onto itself. So one of these, a reflection over one of these lines does not carry the square right back exactly where it is. So let's go through and look at them. So let's look at number 1, x equals 5. Whenever you have a line, an equation that says x equals 5, that means that it goes through the x-axis at 5. So it's actually going to be a vertical line, which kind of, a lot of times students get confused because they think x-axis is horizontal, so x equals 5 should be horizontal. It's actually the opposite. Go through at x equals 5. So I'm going to draw a line. It's a pretty poor line. Hopefully you have a better line. I'll draw again. At x equals 5. Okay, make believe that is a straight line at x equals 5. Okay, it's pretty good. Okay, so if we were to reflect that over that line, well, first of all, this side, the side that's touching the red here, that's going to stay where it is, and everything else is going to move over here. Right? So this point is going to be 1, 2, 3, 4, 5, 6 away from the line. It's going to be 6 over here. And same thing down here. We've done reflections, remember, you just count. And so it would be 1, 2, 3, 4, 5, and 6. All right, so it's going to be 6 on the other side. So right there you can tell that the reflection over that line is not going to carry it onto itself. So right now I'm thinking that's going to be our answer. So I'm looking at number 1 as an answer. But let's go through the other ones. All right, so let's look at y equals 2. All right, so where is y equals 2? Well, again, if x equals 5 goes through the x-axis at 5, and hopefully you see that probably y equals 2 should go through the y-axis at 2. I'm going to draw a line of y equals 2. And you notice it splits this square right in half. So that's a good sign that probably it's going to carry right onto itself. Because all these points, again, it's going to be, so if I take this point up here, the corner of the square, it's going to be 1, 2, 3 units away. So you're going to go 3 here, so that's going to come. So this point's going to just come here, and then this point's going to come here. Well, what are these points down here going to do? They're just going to come back here. So we're going to have a square that's right on top of itself. All right, so that is not going to be our answer because it will, a reflection over y equals 2 will carry the square onto itself. So that's not our answer. All right, then we have y is equal to x. Remember, the only line that, if you have y equals x, it's just going to be a diagonal line, over 1, up 1. All right, so starting at the origin, it's going to be a line. Let's go through like that. Like that, right? And again, you have the same issue that you just had. It's cutting this square right in half, which tells us that the reflection is going to map right onto itself. All right. Now, looking at number 4, you're going to want to put this in y equals form in order to graph the line to be able to see it. So you should be able to do this. It's going to be very simple, one step. We have x plus 4 is equal to, well, I'm sorry, x plus y is equal to 4. And I want to get y by itself, so I'm just going to take x, subtract it, move it over here. Don't do 4 minus x and say like 3 or something like that. You cannot combine those, so it's y is equal to, I'm going to put the x before so we have it in slope-intercept form. So it's going to be negative x, that 4 is positive. So we have negative x plus 4. So our slope is negative 1 over 1. So that's our slope. Our y-intercept is 4. So we can graph that. All right, so we're going to start at 4. So 1, 2, 3, 4. That's our y-intercept. Then we're going to go down 1 over 1, down 1 over 1, down 1 over 1. Hopefully you're doing better with these points. Having a problem here doing these points, but you get the idea. It's down 1 over 1. And again, you have a line that cuts it straight through the middle, or diagonal, cutting it in half, just going the other direction. So again, it looks like our answer of 1 that we got at the beginning was the right answer. All right? So we'll go over the other ones later. And if you have any questions about anything, just ask me in class.